Dear students, in the previous class, I have explained you the working of the standard hydrogen electrode, that is, the reference electrode to measure the cell potentials of various half cells. And I have also explained you the formula to calculate standard electrode potential, that is, E naught is equals to E cathode minus E anode. But when the concentration is not unity, then how to measure the electrode potential? Then we use the Nernst equation. Let me tell you what's that. Nernst equation is E equals to E naught minus RT upon NF, natural logarithm, the concentration of the reduced state upon the concentration of the oxidized state. Let me tell you the use of the various symbols. E. E is electrode potential. E naught, it is the standard electrode potential. R, it is universal gas constant whose value is 8.314 joules per Kelvin per mole. T is 298 Kelvin, that is 25 degrees Celsius. Small n is the number of electrons lost or gained in the redox reaction. F is Faraday's constant and its value which is to be used is 96500 coulombs. The concentration of M solid, that means the concentration of the reduced state, and concentration of Mn plus means concentration of the oxidized ions or the oxidized state. When we substitute the values of R, T, N or F, then we get the value or the Nernst equation as E is equals to E naught minus 0.0591 upon N log. The natural logarithm has been changed to base 10, that is log, concentration of the reduced state divided by the concentration of the oxidized state. This is the equation which you can use in the numericals, and the value of the N will change according to the redox reaction, that is, the number of the electrons lost or gained. While calculating the numericals, you have to keep in mind that the total number of electrons lost is equals to the total number of electrons gained. For that, you have to balance the two equations. Gibbs energy, that is delta G. The Gibbs energy you have studied in your class 11th in unit thermodynamics. Gibbs energy is the energy which is free to be converted into useful work. The delta G is related to cell potential E as equation 1, that is delta G is equals to minus NFE. Delta G is also related to the equilibrium constant K via equation 2, that is delta G is equals to minus RT ln K. E is EMF, delta G is Gibbs energy of the reaction. Combining equation 1 and 2, we can correlate the cell potential and equilibrium constant. Let's see. E naught cell is equals to 0.0591 volts upon N log K, where K is equilibrium constant and N is again the number of electrons lost or gained. Dear children, now let me switch over to the new topic, that is conductance. In our everyday life, we come across normally and majorly two types of substances. The substances which can conduct the current, they are known as conductors, and there are some substances which do not allow the current to pass through them. They are known as insulators. In our daily life, we see that the copper wire, it is a very good conductor. Silver, again a very good conductor. You can say that all the metals are very good conductor of electricity. And plastic, wood, paper, cloth, etc. are insulators. They do not conduct current. In between these two types of substances, there is another category. They are semiconductors. For example, silicon, which conducts current not like the conductors, but they conduct slight current. We will now concentrate on the different types of the conductors. There are two types of conductors: metallic conductors, which are also known as the electronic conductors, and the other type of conductors are the electrolytic conductors. In this unit, we have to concentrate on the electrolytic conductors and electrolytic conductance. But prior to that, let me differentiate between the metallic conductors and the electrolytic conductors. The metallic conductors means the metals. The metallic conductors, they allow the current to pass through them due to the flow of electrons without undergoing any chemical change. The electrons, they move out from one end and they enter through the other end. There is no chemical change that takes place in the metal. Factors affecting metallic conductors: the nature and the structure of the metal, the number of the valence electrons per atom, the density of the metal, temperature. The metallic conductance decreases with increase of temperature. In this unit, we have to concentrate on electrolytic or ionic conductance. That means the ionic compounds you have earlier studied in the first unit of class 12th, that is solid state, that there are substances which are ionic compounds. When they are solid, they do not conduct current. But as soon as they come in the molten state or in the aqueous form, they start conducting current. They start conducting current due to the free ions. For example, NaCl, when it is solid, it will not conduct current because there are no free ions. As soon as we take NaCl and dissolve it in the water and takes its aqueous solution, it dissociates into free ions, that is sodium ion and chloride ion, that carries charge, and it starts conducting current. Also in the molten form, NaCl or all the other ionic solids on ionic compounds, they conduct current due to the motion of the free ions. These ions carry charge. These electrolytes are classified as strong and weak electrolytes. Strong electrolytes are those substances or those electrolytes which almost completely dissociates into ions. For example, sodium chloride, potassium chloride, they almost completely dissociate into ion when we dissolve them into water. Weak electrolytes, they do not and they never completely dissociate into ions. For example, acetic acid, ammonium hydroxide, they never dissociate completely. Now, let me tell you what are the factors on which the electrolytic conductance depends. The first one is the nature of the electrolyte. Just now I have explained you that there are two types of electrolytes, strong and weak. So, if the number of ions are more, as is the case of the strong electrolytes, the conductance will be more. And if the electrolyte is the weaker one, then there will be lesser number of ions and hence lesser is the conductance. Size of the ions produced and its solvation. If the size of the ions is large, if the solvation is extensive and ions become larger in size, then the conductance will decrease. The nature of the solvent and viscosity. If the solvent is polar, then the ionization takes place on a large scale and large number of ions are produced. So, if the solvent is polar, conductance will be more. Concentration of the electrolyte. If the electrolyte is concentrated, the conductance will be less because the motion of the ions will be restricted. But if it is dilute, if the concentration is less, then the volume will be more and ions will freely move and hence the conductance will be more. Temperature. The electrolytic conductance increases with the increase in temperature because we know that the temperature is directly related to the kinetic energy. As the temperature increases, kinetic energy of the ions also increases, and when the kinetic energy increases, their mobility increases and hence the conductance also increases. Conductance of the electrolytic solution. Now let me explain you few terms. Resistance. It is the obstruction to the flow of the current. When the current flows through a conductor, the conductor offers some resistance or obstruction to the flow of current. The symbol for resistance is R and its unit is ohm. Wheatstone bridge is the instrument which is used to measure the resistance. Resistance R is directly proportional to the length of the conductor and inversely proportional to the cross-sectional area A of the conductor. R is equals to rho L upon A. This rho is proportionality constant known as resistivity or specific resistance. By convention, we give preference to resistivity over specific resistance. The unit of the resistivity is ohm meter. Resistivity is defined as the resistance when the conductor is 1 meter long and its area of cross section is 1 meter square. The symbol for resistivity is rho. Conductance. Conductance is the reciprocal of resistance. It is the ease with which the current flows through a conductor. Its symbol is G. Initially its symbol was capital C, but it has been replaced by G because capital C is used as a symbol for coulombs and concentration. So now we use G as a symbol for conductance. Conductivity cell. Conductivity cells are specially designed cells in which the electrolyte is filled. Dear children, as you know that when we take a metallic conductor in the form of a wire, we can tie its end. But in case of the electrolytic conductor, since it is in the aqueous form or it is in the molten state, we cannot tie its ends. So we have to take some apparatus, we have to take some vessel in which we can fill the electrolyte or the molten or aqueous solution. So we use the conductivity cell to measure the resistance, resistivity or conductance. As I have explained you that the conductance is the reciprocal of resistance, similarly the reciprocal of the resistivity is conductivity, also known as specific conductance. Again here, as per by the IUPAC convention, the term conductivity is preferred over specific conductance. Its symbol is kappa. The alphabet is just similar to alphabet K. So we can say that the conductivity is the reciprocal of resistivity. So we can modify the formula as R is equals to rho L by A can be written as L by Ka. This K is kappa. L by A is cell constant G star, or you can say that G asterisk. Its unit is meter inverse or centimeter inverse. Conductance, cell constant and conductivity are related as conductance into cell constant equals to conductivity. You can use this formula to calculate conductivity or resistivity or resistance. So dear children, just now I have explained you the Nernst equation to calculate the electrode potential at any concentration, and I have explained the various types of conductors, the metallic conductors and electrolytic conductors. I hope everything is clear to you.